Hi everyone. Today's topic is variables. This is the second lecture about mutation. First, we are going to talk about the operational semantics of the language that we learned on Monday. The language name was PFAE. Remember? The language was PFAE. FAE with boxes. So on top of the usual FAE, we extended the language with 3 language constructs for boxes and another for sequencing. And we said that we added sequence of 2 expressions so that we can have interesting examples for boxes. The semantics of E1 semicolon E2 was to evaluate the first sub-expression, throw the value away, evaluate the second sub-expression, and that's the value of the sequencing expression. That's the semantics. For boxes, there's 1 language construct for introducing boxes and 2 language constructs for using boxes. New box with an expression meaning that we are constructing a new location in the memory. So that's represented by an address in a memory. And then in that address, we initialize that address with the value of this expression. In some languages, not every name is initialized. So initialization is really important. In languages that we construct, we always require the initial value. In some languages, they do not require initial values. Like what? C or Java. You can just introduce, say, int x. That's it, right? In C, then that's going to be null. In Java, null is the default value for any object. So when you just introduce some name without any initial value, that's going to be null by default. It's really bad semantics. So C has many bad features, and it's really difficult to write correct C programs. If you found difficulty in C programming, that's not your fault. That's the fault of the C programming language. C is not for any programmer. C is for the programmer who understands the memory usage, who knows how to write secure programming. And the C programming language is really good for, performance. And in order to take advantage of the performance in the presence of these errors, really easy to make errors. We call them error prone. I used this term before, right? Error prone. It's easy to make errors in C because C lets programmers, use memory locations using addresses. Addresses are values in C. You can add numbers, multiply numbers to addresses, and then you can just access random place in your memory and corrupt it. So hackers really like to hack C programs, attack C programs, because as soon as they have a control over return address of a function, they just got your computer. They can do anything on your computer. And because C has that many errors because of the memory management, right? Managed by people. Java and other languages with runtime memory management system, they have garbage collection that we are going to discuss after the midterm exam. But still, Java has really strong type system and it has really good features that we can discuss later. But the biggest problem with Java is null. So Java type system can catch many errors from programmers, mistakes. They're really good. But once you have null dereference error. Oh, welcome to the hell. It's really difficult to catch the error and fix the problem. That's null pointer exception, in other words. If you see that, wow, null is everywhere because, as I said before, if you do not initialize a name with a value, then that's null by default. Everything is null, right? So it is really bad. So good programming languages require programmers to have this initial value. When you construct a new location reference, then we require people to use the initial value. The initial value may mean nothing, but still, it's not going to give you a null pointer exception. And set box, meaning that the first sub-expression should represent an address in the memory, and the second sub-expression should denote the value in that address, meaning not an old value in that address, but the new value that we want to put on that address. And finally, open box, meaning when we evaluate this expression, there should be a location, the address, and when we go to the store, go to the memory using this address, then we can get the value in that address. So how can you write that in the operation semantics? Addresses, let's call them A for address, L for location, whatever you want to say. But in this notation, we decided to use A for address. In the Scala implementation, type address is actually integer, but we do not need to show that. We do not need to reveal that fact in this operation semantics. Here, value V is either num V or closure V or box V, right? Num V, which has an integer, closure V, which has a parameter name, body expression, and the environment, and box V using the address, containing the address. And store is a map from addresses to values. And we're gonna use M memory for store. Using that notation, our new template for the operation semantics is under this environment and this given store. When we interpret this expression, its value is V, and while evaluating this expression, we may have changed it store. So because it's a template, we use same M here, but it doesn't say that this and this M and this M is the same. It's not like that. They may be the same, but we do not guarantee that they are going to be always the same. When we interpret number expression under some environment and some store, we don't even use the environment and store to evaluate an number expression. Whenever we have a number, we just construct number value num V, and the store didn't change. How can you say that in the operation semantics? Under whatever environment, under whatever store, evaluating a number N does not change the store, just the same. This time they're really the same, right? And the value is N. That's how we write this implementation in Scala to operation semantics. What about addition? For addition of L and R, we interpret the first sub-expression under the given environment and a given store, which is gonna result in a pair of a value and a store. We are gonna interpret the second sub-expression using the given environment and the resulting store from the previous evaluation. Then the result of this addition of L and R is going to be the value of addition of LV and RV and the resulting store from evaluating the second sub-expression. Right? We already saw that on Monday. How can you write that in the operation semantics? Simple. Under a given environment and a store, evaluation of E1 plus E2 is what? under the given environment in a store, we are going to evaluate the first sub-expression whose value is going to be a number, and it may change in the store, so we are going to use a different name, M1. Note that it's going to be N1. If you say V1, that's wrong. Why? I'm going to be back in a minute. Under the given environment and under the resulting store from this one, yeah, right? We are going to evaluate the second sub-expression. Again, there should be a value which may be the same with N1 but may be different, so we are going to call it N2. And the store, this M2 may be M1, right? It may be just the same, but because we don't know for sure, we are going to give it a new name, M2. Right? Again, this N2 cannot be V2. Then the result is going to be N1 plus N2, and the resulting store is going to be what? This M2, right? The final resulting store. You know that V is either one, N number, or closure V, or address. So if you say V1 and V2, and here instead of that you say V1 plus V2, it's wrong, because this V1 may be closure V, V2 may be address. We don't know how to add closure V with whatever. We don't know how to add an address with whatever. Actually, in C, we know how to add a number and an address, but not in PFAE. Okay, that's the point. Again, later, when we have a cool language like CFAE, and it says FAE with C-like features, and then we have several semantics in prose, meaning in English, then you may need to write down these differential semantics for that language, but not today. What about identifier lookup? Identifier lookup, it's going to look up the environment using the name, and just the name cannot change the store, so it's going to be just the same. Meaning that under a given environment in the store, the value of an identifier, we do not even need to look up the store. We only need to check whether the given environment has access value. If so, we look up the environment using the name, get the value, and the store remains the same. Okay, so far so good. How about sequencing? Yeah, right, sequencing. We are going to interpret the first sub-expression under the given environment in a store. And then we evaluate the second sub-expression using the given environment and the resulting store. And that's it? Yeah, that's it. Then what's the result? Yeah, that's the result. How can you say that? Let's see. How can you say that? Under the given environment, under the given store, when we evaluate E1 sequencing E2, meaning E1 after E2, then how do you evaluate it? Under the given environment, under the given store, evaluate the first sub-expression, get the value, this time V1, not N1, right? If you say N1 here, it's wrong. I will tell you more about that in a minute. And then possibly change it, store. And we are going to interpret E2 under the given environment, and then the resulting store, right? The resulting store. Evaluating that may result in some value V2. Again, that cannot be N2, right? And possibly change it, store. Then the value of this sequencing expression is V2. The result of the second sub-expression. And actually, the resulting store M2. meaning that the result of evaluating E2 is the result of evaluating this sequencing. That's why the result of evaluating sequencing is evaluation result of the second sub-expression. But because we need this store to evaluate R, and because evaluating L may have some side effects, we need to evaluate L first and then R. Oh, do you see that? Do you see that connection? Previously, we said that the premises on top, they may not have any ordering relation. But here, there's a clear ordering relation because in order to evaluate E2, we need M1, right? So we need to evaluate this first and then the second one. So first, good. I emphasize that you cannot or you should not call them N1 and N2. Right? Why? What's the problem? When you have sigma m and E1 semicolon E2, and what's the value of it? And you say, oh yeah, under the given environment and a store, I'm going to evaluate the first expression. Its value is going to be N1. And you say under the given environment and and M1 and the resulting store M1A. Let's make it clear. Oops. N1, M1 and under the given environment and that resulting store M1, we are going to evaluate E2 whose value is N2 and M2. Then I'm going to say, that's the result. The result of the sequencing is the last one, so N2, M2. What's wrong here? By writing this rule, you are basically avoiding, or rejecting the semantics of evaluating E1 resulting in an address or closure V. Let me repeat what I just said in Korean and repeat again in English. 이걸 N1이랑 N2라고 하면은 완전히 다른 언어가 돼요. 언어가 그냥 시멘틱스가 달라요. 이 위에 있는 보라색은 뭐라고 그랬지? E1을 계산한 밸류가 V1이니까 얘는 넘버일 수도 있고 클로저 V일 수도 있고 어드레스일 수도 있어요. V2도 마찬가지예요. 또 아무 밸류나 올 수 있는데 얘를 N1이라고 N2라고 하는 순간 이 언어는 시퀀싱은 항상 넘버만 나오는 애야. 전혀 다른 애예요. 그러시면 안 돼요. As soon as we have N1 and N2 here, the semantics of this red rule is different from this one. Different language. This semantics is not PFAE. It's some different language. Two languages have different semantics. Clear? Yeah. Then our BFAE interpreter explains state by representing the store as a value, right? This inter function took three arguments: expression, environment, and a store, meaning the store is a value. Just like an expression and an environment, store is, it's a value. The third argument value of this inter function. So every step in computation produces a new store, meaning the result of calling this inter function is a pair of V and another store. So it's a new store. So every step in computation produces a new store. So this interpreter itself is a purely functional, meaning that this interpreter, when we call this inter function with the same arguments, same expression, same environment, and the same store, the result is going to be always the same. That's what we meant by purely functional in the first part of today's lecture. Remember? Yeah, that's what we learned before. So it's called a store passing interpreter. An interpreter that passes store as a value. An interpreter that passes a store as the third argument value. Okay? Okay, so variables. I told you that in the language that we learned so far, it was BFAE. Actually, this BFAE is not non-functional enough, meaning that like something to be like a C programming language. 이게 C 프로그래밍 언어처럼 뭔가 임퍼러티브해지기에는 2% 부족해요. Yeah, it needs something. What? That's variables. All we used was boxes, right? And these boxes do not explain variables. Variables meaning that this is a global variable. Counter, it's a name and its value is 0 and the value of the name, that's being changed. Are you with me? Our three language constructs, right? That box E and E dot set E and E dot get, they are just values. They make address values and they just use them as values. They do not change the value of variables. They do not change the value of this name. In a program like this, like that, an identifier no longer stands for a value. An identifier's value is not fixed to that initial value, but it stands for a variable, meaning its value keeps changing. Let's look at this example. So the previous example can be implemented by using boxes, meaning that we can interpret or we can describe the semantics of the variable by using boxes, making box to have some variable, right? And then, hey, counter, your initial value is 0 and I'm going to keep it in this box. So explicitly make boxes. And, do you want to change the value of the variable? Then everything is boxes now. X is box, get the value of X and get the value of counter and add them and put the value into counter. And whenever you use it, get it. Okay? And when you call a function, you always pass the value inside the box, meaning you always make boxes whenever you pass values. Boxing, it's called boxing, meaning you are wasting memory. Whenever you pass numbers or any values, you need to box it, you need to unbox it. Oh, that's annoying. Even though we can simulate the semantics, right? That's too bad. What's gonna be a different option? Option 2 is essentially the same, meaning essentially we are using boxes, but not by the programmer, but by the language. Hides the boxes in the interpreter, meaning that it could be a new language. BFAE plus variables, we call that MFAE. M for mutation. Now really mutation. And we can add a new language construct saying changing the value of the name. Wow, that's a brand new thingy. Here ID, it's a name whose value can be changed by this assignment expression. Okay? It's different from this set expression. This set expression meaning that the value of this expression should be a box, meaning an address. But this one is what? It's an expression, but this one is name. We can change the value of a name, of the identifier. This is the main technical meat of today's language MFAE, and we are going to talk about this semantics after the first break.